Good morning. It is 12:15 in Philadelphia, and welcome to Thermal Live 2017. I'm Graham Kilshaw with Electronics Cooling Magazine, and we are the creators of Thermal Live. This presentation is brought to you by Celsia. The title of today's presentation is Heat Pipes and Vapor Chambers, Useful Guidelines for Heat Sink Implementation. And your presenter this morning is Mr. George Meyer, the CEO of Celsia, speaking to us from San Jose. Morning, George.
Morning. Thanks, everybody, for attending, and good morning or good afternoon, depending on where you are.
Yeah, I see people logged on
from all over the place.
Yeah, from all over the world. Looks like a good crowd this morning. And we'll be joined later in the presentation by MP Divakar, the Senior Digital Editor for Electronics Cooling Magazine, who'll be joining us for the Q&A portion of today's presentation. Attendees, this is about a 35-minute presentation, followed by a question and answer session. You can enter your questions at any time during the presentation, and if you're not familiar with this particular webinar platform on 24, here's how you use it. The way to enter your questions is the Q&A button at the bottom left-hand side of your screen. Click that box, enter your questions at any time. We'll see them coming in, and we'll do our very best, George, myself, and MP, to answer those questions at the end of the presentation. If you have any technical issues during the presentation, just refer to the yellow tab on your screen. Most of the common issues with webinars can be solved there. One of the very nice things about this platform is you can actually chat with other audience members. If you click on the group chat button, you'll see everybody that's logged on today, and feel free to ask questions of your colleagues and peers who are attending today also. But please don't use that question to send questions for the presenter. Questions for the presenter go in the Q&A box. Last couple of items. You'll see two links at the bottom of your screen, then the shape of a chain link. The first one is a link to the Thermal Live website. You still have plenty of time to register for the remaining presentations today and tomorrow. I believe we have 10 presentations in all during this two-day event. And the second link is a link directly to the Celsia website. And last but not least, I know everybody's always asking us, will the slides be available after the presentation? And the answer is yes. You don't need to email us. You don't need to do anything. We will automatically send you the slides at the end of George's presentation. And with that, I'm going to hand over the reins to George, and let's begin the presentation. George, over to you.
We'll do that. Thank you, Graham. And, of course, we're going to start things off with another question. We got a couple questions embedded in here, and it's just sort of to get an idea of and for example, this one. Do you currently have a good understanding of when and how to utilize vapor chambers as opposed to heat pipes? So we just kind of get a feedback from the audience as to what their expertise level is. So if you can go ahead and vote on that, and we'll take a look at the results later on today. In today's webinar, we're going to basically have six areas that we're going to talk about. And the first one is, do I need to use two-phase? And we'll look at sort of the benefits and consequences of using solid materials as opposed to two phases. We'll look at some basic rules of thumbs, and then we're going to talk about vapor chambers. And always the question is, are they just flat heat pipes? And we'll answer that question, of course. We'll take a look at some sizing. We're going to talk about how do I integrate them. We're going to talk about the heat exchanger, in other words, the getting rid of the heat part, and how you design those, and what, from a construction standpoint, what they look like. And then finally, what about thermal modeling for these devices? We're going to talk about that. So we're going to cover all that stuff today. Moving on, when to use two-phase device. And the short answer is always when your design is conduction limited. Because obviously you're not going to move away from a piece of metal to something else unless there's a reason to. And in this case, it's always the conduction limit that's reached. There's other reasons you may want to use it. Non-thermal goals, as we say, such as weight or size. Sometimes the vapor chamber or heat pipe devices can be smaller or lighter than its equivalent performance in a solid material. And we have three examples here. we took a look at, in the same application and the same format heatsink, same airflow, same power, everything is held the same, an aluminum heatsink, a copper heatsink, and then a heatsink with a vapor chamber embedded into the base. And just to give you a quick idea on the comparison of these, if we look at the aluminum, the conduction loss and the delta T due to conduction in the base is about 22 degrees. If you go to copper and you keep the base the same thickness, that's just going to cut it in half to 11 degrees. Often what happens is they will reduce the thickness of the base to get a little more thin area. And so in this case, there was 17 degree delta T. But if you keep everything the same, the copper has twice the conductivity. So somewhere between 11 and 17 degrees for the copper version. But if you put a two-phase device in it, the conduction loss is only 4 degrees. So you can see why you would go to using a two-phase device. So let's look at some rules of thumb. Everybody knows that the two-phase devices are incredible heat conductors. And, people talk about huge multiples of better conductivity than aluminum or copper, 5 to 50 times. I think for us, for this audience, the numbers, the watt per meter K numbers are more important. If I'm doing sort of a local spreading, you might be down in the 1,000 watt per meter K range. And if I'm moving heat across the room or some distance away, you can get those higher numbers, the 50,000 numbers. We say that heat needs to be moved more than, I generally say, an inch and a half to 2 inches, but 30 to 50 millimeters before you look at using two-phase over a piece of metal. There's a couple other reasons, rules of thumbs. If you're interested in spreading heat to reduce a hot spot or attached to a local heat exchanger, the ratio of heat spreader to heat source should be on the order of 20 to 1. In other words, the area of the heat sink versus the area of the device being cooled. Anything less than that, generally metal, is good enough. And when you're designing with a heat pipe or a heat sink or a vapor chamber, we always leave 25% thermal headroom. In other words, for a 100-watt heat pipe, I will use that as a 75-watt in application. So I always leave that margin. So I think everybody has seen these slides. Probably everybody understands how these things work. The key takeaway that you want to keep in mind here, because in the question I generally get, is these devices are vacuum devices. So they do work below the working fluid boiling point. And that the limit to the performance of these things is usually the capillary limit, and that is getting the fluid to be returned back to where the heat is taking place. Let's talk about the wick structures, since we're talking about the capillary limit. There's 3 common wick structures that are used, and if I had to say percentage-wise in the market, probably high 90% of the heat pipes in the marketplace use the sintered powder. The other 2 common ones are screen and grooved wick structures. You can see the power density variation differences between the 3 designs, the thermal resistance, and the orientation. So the sintered wick is good for high power densities. It generally has fairly low thermal resistance, and it's good in working in any orientation. If you look at a screen wick, it won't handle as much power density. In fact, relatively low, less than 30 watts a square centimeter. The nice thing about a screen wick is that it's used when you need a higher Q max. It will move more liquid in a horizontal application. And groove is just really the lowest cost structure you can make. And this slide talks you through some of the performance limits. As you can see, the primary limit is always the capillary limit, and that goes along with the previous slide when you're talking about wick structures. This shows a calculation for a sintered wick heat pipe. So you can see that the capillary limit in the temperature range of electronics is the limiting factor. It talks about the other limits, but we don't need to go into those in great detail. What's important to see here is when we do a look at the performance of these devices, and these two charts, what we're showing is the chart on the left are heat pipe performance limits, and the chart on the right, the vapor chamber, and it's by diameter for the heat pipes and for width for the vapor chambers. The blue line will show you on the heat pipe, will show you the vapor limit, whereas the red line will show you the wick limit. So you can see that the wick limit is the limiting factor until you start to flatten the heat pipes. And once you start to flatten the heat pipes, then the vapor limit generally comes down to be in line with the wick limit. In fact, when you're making ultra-thin devices, that's one of the things that you need to optimize, and that is the sweet spot between the wick limit and the vapor limit. And if you look at the vapor chamber chart on the right, you can see that we have the wick limit is above the vapor limit, and that's just because these are flattened devices. And the vapor space itself is smaller when you're looking at a rectangular device versus a round device. Here's some information on the wick structure. So we're seeing two photographs of sintered wick structure. The one on the right in the tube is what we would call just a standard wick structure. And the porous wick structure, the post one is a more open wick structure. Depending on the application, you can vary the porosity and the particle size of the wick structure to give you different performance. So you really can't just say, okay, take a look at the heat pipe, the published data from heat pipe manufacturers, because the wick structure can be tuned to meet a certain application. It's just like designing a car for a particular application. If you want to go fast or if you want to go off-road, you do different things. You can change the wick thickness, you can change the wick porosity, you can change the working fluid. So a lot of things you could tweak to match the performance of these devices to the requirement of the application. So that's the key takeaway. So how does orientation affect the performance of these? It's a very common question. A lot depends on the wick structure and whether it was designed to work against gravity. So we have a chart here that shows you the performance of these different diameter heat pipes versus the gravity angle. And we go from a positive 90-degree angle where the heat source is at the bottom and the cooling is at the top, to the minus 90 where that's turned around, where the heat source is at the top. And you can see that once you get to, say, minus 30, the performance really drops off. A lot of this is a function of the length of the device. And what we really wanted to show you is if I take my 8mm heat pipe, so we have two lines for 8mm, blue line and a red line. So we've done some gravity optimization on the red line for the 8mm, and you can see how that works much better against gravity. Moving on to effective thermal conductivity. We call it effective thermal conductivity because the conductivity of these things will change depending on the application. So for any particular application, we can calculate what an effective conductivity would be. And what we wanted to show you here was how that number changes. So we've put together a little thermal assembly here with a couple of heat pipes, and all we've done is change the length of the heat pipes. So the power per heat pipe is the same. So we go from a heat pipe at 75 millimeters long up to 200 millimeters long, each of those carrying 25 watts. And the conductivity numbers go from 6,600 watt per meter K up to 28,000 watt per meter K. So you can see if I extended this thing another 200 millimeters, how you would start to get to rather large numbers. But for most electronics cooling applications, you don't move the heat much more than about 150 to 200 millimeters. And for local spreading uses, the 6,000 number is pretty typical. Okay, what is the difference between the most common versions of these devices? Heat pipes, vapor chambers. Heat pipes are heat pipes. They're round heat pipes. They're generally available in 3 to 10 millimeter diameters. Although for power electronics applications and other applications, we've made them up to meters in diameter. Power electronics, 3/4 or 20 to 25 millimeter diameters are not unusual. Then there's two other types of vapor chambers, what we call a hybrid one-piece vapor chamber that is really made out of a large diameter tube, and a traditional two-piece vapor chamber, where the two pieces are stamped, the wick structure is put in both pieces, and then it's sealed, generally welded the whole way around the periphery. This just gives you some typical dimensions, how to mount them, the relative cost of the devices. So we talk a lot about moving and or spreading heat, and what is the difference between those two, and what effect does it have on your design? Generally, moving is when you have a heat sink that's located remote from your device, your hot device. We call that moving heat. So you're moving it from point A to point B. Spreading heat is where your heat sink is located at the area where your hot device is, but the heat sink is much bigger than your device, so we call that spreading. With the heat pipes, what you do is you get a linear flow, heat flow. You get moving heat from point A to point B. In a spreading application, you are spreading heat in all directions. Occasionally, you want to do both. For example, if you have heat pipes say you need 5 heat pipes for a particular application, and those 5 heat pipes won't fit underneath your heat source, then you're going to have some conduction issues in getting the heat spread to those heat pipes. You got attachment issues between the spreader and the heat pipes. In those cases, a vapor chamber can be used to do both spreading and moving. So it's not exclusive. Heat pipes are used only for moving, and vapor chambers are used only for spreading. You can mix and match those things depending on the application. And here we have question number 2 for the day. Does your company currently use heat pipes or vapor chambers? Obviously, we're looking for answers as yes, we use them, and we're thinking about using them, and no, we have no plans on using them. And we will move on to the next one, 17. This is a new platform, so bear with me as we sort of learn how to use it. When moving heat to remote heat sink, this is probably 99% of all applications that are out there, because from a volume standpoint, most of those applications are in computing applications. Complex shapes are often required, as you can see in the photograph. Heat pipes can be bent relatively easy, just as easy as a piece of copper tubing. They're available in volume. The manufacturing capacity in the world is many, many millions per month. The work against gravity is not too bad. Generally, we'll say, for example, for a laptop application, they'll work against gravity, say up to a 45-degree angle. Satisfactory for most of those applications. And in this particular application, it's a notebook computer. You can see where there's 2 flattened heat pipes used to cool 3 heat sources. And what they're doing is they're just daisy chaining the heat pipes to move the heat from multiple heat sources. That's fairly common, is to use multiple heat sources on a particular device. So when we talk about spreading heat, in this particular case, we're spreading heat to what we call a local heat sink. In other words, it's not a separate heat sink that's located somewhere else. You can use heat pipes. Heat pipes are actually a good choice. If you've got reasonable airflow, you've got plenty of room for fans, you've got nominal power densities. In other words, if it's not a very challenging application, heat pipes make pretty good spreaders. And here's an example of one for a telecom application. Where 4 heat pipes were put into the base of the heat sink just to move the heat off to the side where the heat sink has been extended. Now, we will occasionally use vapor chambers for spreading on a local heatsink also, just like heat pipes. Vapor chambers really are the best choice if you really limit it in your space, your Z, generally that's Z, your height is limited, or your power densities are high, or your airflow is low, or it's just a challenging application where you need every degree you can get. In this example, what we've done is we've taken a heat pipe design from a previous generation of graphic chip coolers. Obviously, the power densities and the powers have gone up for the next generation, and they wanted to use the same basic shape and form factor. So we replaced the two 8mm heat pipes with one vapor chamber. And what that did is it gave us a 6-degree better cooling versus the original heat pipe design. And the reason for that was just better spreading and, in this case, more fin area, because the bent heat pipes took up some space for the fins. And here's another example of vapor chambers used to move heat to a remote heat sink. Challenging application. Laser diodes for a very, very high-end 3D projector. 3 laser diodes for the 3 RGB for the 3 colors, and a common heatsink for all 3. So heat pipes, vapor chambers are used for spreading heat. There's just sort of some oddball examples we wanted to throw out there for you. Example one is a sort of flattened heat pipes that are flattened and soldered into a base, and the heat pipes are machined. Often this is used to, as best possible, get what they call direct contact. The heat pipes make direct contact with the heat source, eliminating the 2 interface layers. Works pretty well. The machining of those heat pipes, you really need to know what you're doing to not have an issue with machining of the heat pipes. But it's rather common that it's done. Example number 2 shows an area where they wanted to upgrade the performance of that particular heatsink. It moved to the next generation processor, the i7 chip. There was a copper base on those 4 heat pipes, and that was changed out to use a vapor chamber, and they picked up 5 degrees better performance. Most of that had to do with the increased power density with the i7 chip. So let's talk a little bit about bending and shaping. As we mentioned earlier, heat pipes are very flexible. No real difference than bending simple copper tubing. Some rules of thumbs around that are the bend radius is 3x the diameter of the heat pipe. You can push that a little bit down to 2.5 or 2. The 3x the diameter is a good place to start. Each 45-degree bend reduces the Qmax by about 2.5%. So keep in mind that as you're doing this bending, you are reducing the performance of the heat pipe itself. You can flatten the heat pipes to generally about 1/3 of the original diameter. So for a 6mm heat pipe, you can generally flatten those to 2 millimeters. You can machine the wall if you're careful. For example, the picture to the left shows these 6 heat pipes in a base that are machined after they've been installed and flattened. If the heat pipe wall thickness is thick enough that you can take off maybe 1/10 of a millimeter, then you can do the machining. Some of the heat pipes on the market today have 0.3 millimeter wall, and you really don't want to machine those because you're just getting the wall too thin. So the one-piece vapor chamber, because it's made out of a big tube and flattened, you can bend them. You can bend them, along the narrow plane, as you can see in the pictures. The bend radius is typically 10 millimeters. These particular tubes are flattened to 1/10 or 1/20 of the original diameter, but they're designed that way, so they're designed that they can be flattened to that extent. Surface pedestals can be formed into the vapor chamber to for either to extend above the vapor chamber to reach into a recess for the heat source, such as in a processor that's got a stiffening ring around it. And the last one to look at is the two-piece vapor chamber, where you're using two stamped parts that are then put together. It gives you more flexibility on the bend, so the stamped bend can be 1x the thickness of the sheet metal. You'll pay a pressure drop penalty for that, but it's what we call a step, and you can see that in the picture on the left. So the upper and lower plates are stamped flat, and then the wicks put in. Stamped pedestals up to 3 to 5 millimeters tall are possible. Then these things are welded up and processed just like any heat pipe. Let's go on to sizing these devices. Based on what we call a typical wick structure, we've taken a look at the common sizes of heat pipes and giving you a guideline as to sort of the typical Q maxes, what these things can be flattened to, what's the resulting width once you flatten them, and what happens to the Q max when you go through flattening. So you can see, for example, on the 3 millimeter, your Q max is typically in the 15 watt range. 3 millimeters are commonly flattened down to 2 millimeters. The resulting width is 3.57 millimeters wide. And if you flatten these, assume that you're down to about 10 watts in Q max. So we've given you those numbers for the common sizes. And let me walk through an example here. What do I do with that information? I've got a 70-watt ASIC that's 20 by 20 millimeters, and we're going to move the heat with 190-degree bend. So if I look at 3 6-millimeter heat pipes, so that gives me 18 millimeters in width for a 20-millimeter heat source, so good coverage on the heat source. If I look at the Q max per heat pipe, we're at 38 watts, so times 3, so I got 114 watts of capability. If I assume a 25% safety margin, that means I can do 85 watts, plus loss due to bending, two 45-degree bends, one 90-degree bend. So my performance for those 3 6-millimeter heat pipes is at 81 watts. So we're okay because we have a 70-watt application. The other option would be to use 2 8-millimeter flat heat pipes, and we do the same calculation here. Is what's the Q max per heat pipe, and then the total, and then if I run a 75% margin, so I'm down to 74 watts. So either of those two designs would work in this case, thermally work, and you can see you get pretty good coverage on the heat source itself. We're going to jump into mounting options, and we're going to go through this quickly because the mounting options for heat pipes and vapor chambers are the same as any other heatsink. Okay, we just showed you some examples here. The upper right-hand corner is a notebook application where they're simply soldering the two heat pipes to a stamped-out spring clip that's probably uses push pins or screws to hold it down onto the board and onto the device. Once you get up into sort of higher end applications, higher power servers and things like that, you move up to the typical screws and springs. The heat exchanger design used for these devices is no different than what's used in just typical heat sinks. You can use extruded heat sinks, die-cast heat sinks. You can use bonded fin, skied fin, fin packs, forged fins, machined heat sinks. I think the most common that are used in the marketplace is probably fin packs because they're used in notebooks, and machined heat sinks that are used in really high-end applications. So the most common ones are the fin packs and the machined, although you can use any of these with heat pipes and vapor chambers. Assembly attachments, I think that's safe to say that over 90% of the applications use solder. It does a couple things. One, it gives you a good mechanical joint as well as a good thermal joint. And the key there is the thermal joint. The aluminum parts are nickel plated so that they're directly soldered between the copper and the aluminum parts using the nickel. Sometimes we will use a thermal epoxy. Often that's used when the power densities are relatively low and the parts are relatively large. So either of those are acceptable. The soldering is going to give you a better performance. Let's walk through the design process for these things. So what we normally do is we'll estimate the size and number of two-phase devices to manage the heat, spread or move the heat. We'll generally oversize those by about 25% to take up for any variation in operation, orientation, or power, or any of that kind of stuff. We'll estimate the size of the heat sinks that's required to dissipate the heat. Then what we do is we move that into an Excel model so that we can do some what ifs, if I make the fins longer or shorter, that sort of thing. Once we think we're getting close, we generally move that design then into a CFD model, and then obviously build something and get some test data. Step one is always to do what we call a volumetric calculation. So you're sitting in a meeting where they're talking about the next product that you're going to work on, how much power that you're going to have to take care of, and how little space they're going to give you to do that. The volumetric calculation allows you to get pretty close to a size that's required to do your cooling, based simply on a couple of numbers that you'll have early on in the design phase. Generally, you'll know the power that you need to get rid of. You'll know the delta T or the ambient that it's going to be in, so the available delta T. So for example, if I've got 800 watts, I've got an available delta T of 40 degrees C rise above ambient. You often know how much airflow you're going to have, so moderate airflow, no airflow. In this case, we're using moderate airflow, 2.5 meters per second. So you can do a quick estimate as to how much volume is going to be required for that solution. So if you do the quick calculation, it says, hey, I need 2,300 centimeters square, convert that to inches cube. I can need 140 cubic inches. So you can get an answer in a couple minutes as to how much space that you think you're going to need. How close is this to reality? Well, the final design for this particular application was 120 cubic inches. So the good thing is it over-predicted the space you needed a little, but it's within 15% of what the real solution turned out to be. That's close enough for that phase of the design. The next thing we'll often do is do the same thing in an Excel spreadsheet. In an Excel spreadsheet, what we do is we just take a little more detailed look at the individual pieces of the design. I see I have just a couple minutes, so we'll move along here. So we take a look at the heat input, we take a look at the TIM, the interface material, what's its resistance, what's its delta T. We do some conduction estimates. We do some estimates on the delta T on the heat pipe or vapor chamber. And the key thing is to look at the heat exchanger design, the fin area and the airflow. The nice thing about this is it breaks it down. It says, hey, look, here's your bits and pieces. Your TIM is 7 degrees, your base conduction is 17, your heat exchanger design is 18 degree delta T. And you can see that when I vary that from just an aluminum heat sink down to a two-phase heat sink, my 17 degrees goes down to 4 degrees. This generally will get within about 10% of the final solution, but it allows you a whole lot of flexibility to do what-ifs just by changing some quick numbers. obviously, the next step is to go through a CFD analysis. I don't think we have to talk about the benefits and drawbacks of that. I think there's a presentation from Mentor that's going to go through some of that stuff. So one of the potential drawbacks of that is you have to have enough validation of your model before you can rely on it. So always validate your model. Either you have enough information from the previous design, or before you believe this, you want to build and get some real data. I think the last question of the day. How much thermal design assistance does your company require or expect from its vendors? Virtually none. We have our vendors build to print. Some feedback from the vendors is nice, or we rely a lot on third-party or vendor thermal engineers for their expertise, or obviously don't know. And so that's the last question of the day. And if we go to questions and answers.
Thanks, George. Great presentation as usual. We do have quite a few questions. And
okay.
Attendees, if there's questions you're thinking of, now's the time to enter them. We're up to 12 questions so far. Let's see if we can get through them all. Attendees, if you want to ask a question, just use the Q&A button at the bottom of your screen and send them in right now. All right, George, let's see what we can do. First question comes from Jose at Intel. Do you have a catalog of HP and VC and their capacity based on the size, length, and flatness?
No. Sorry. Because these things, the performance of these things change as soon as you change any of the attributes of the application. If I change the heat source size, if I change the heat sink size, if I change the airflow, if I change any of those things, the performance of the heat pipe or the vapor chamber is going to change. What we generally do is say, we'll give you some guidelines. When you have an application, call me and I'll give you the number.
Okay, and I think we'll do some follow-up on these questions outside of the presentation as well, so we can get those contact numbers back to everybody. Next question, George, comes from Russell at Bluecore. Don't know if you can answer this question or not. Out of interest, how are the wicks manufactured inside the copper tubes? Can we answer that one or not?
Yeah, we've got a bunch of little elves that do that. No, I'm kidding. It's depending on the wick. In other words, a groove wick is going to be put in during the manufacturing of the tube. Either they draw the groove into the tube, or they will what they call swage the tube over a mandrel and put the grooves in. The screen, if you're using a screen wick, is just cut, rolled up, and slid in, and often then expanded to touch the wall well. The sintered wick is actually poured in as a powder and then goes through a sintering process, so the powder sinters to the wall and sinters to each other, the powder itself.
Okay. Hey, George, just a heads up, we're up to 20 questions right now. I don't know how far we can get, but let's give it a shot, see how many we can get through. Next question comes from Mark Smith. What's a good rule of thumb for derating heat pipe Qmax based on flattening, bending, orientation, etc.?
I think we touched on some of that in some of the earlier slides. Bending was about 2.5% loss for every 45-degree bend. Flattening affects more the vapor Qmax for the vapor than it does the wick structure. So flattening, unless you flatten beyond the wick capability, flattening generally doesn't have a big effect on the performance. But I think, like you said, we'll come back and answer all of these in detail over the next few days, and send them out to everybody.
Yeah,
so go ahead.
If we can touch on as many of them as we can, and then we can do detailed answers for everybody. I think after today's event, we're now up to 23 questions. Okay, 2 questions here from Hazem. His first question is, can we derive an accurate lumped thermal model for heat pipes and vapor chambers? I'll let you answer that first, George, then I'll go to his second one.
I'm not quite sure what you mean by lump, by probably bulk, I'm assuming. Can we derive an accurate bulk thermal model for... I'm not quite sure what you're asking there, Hazim, but
let me try a second question that might shed a little bit of light. His second question is CFD reliable to model vapor chambers of two-phase heat spreaders?
Yes and no. In other words, if we go through the calculation and I tell you what its effective thermal conductivity is in a watt per meter K number, then CFD is a perfect place to do it. If you're trying to model the liquid flow in the wick structure, the boiling flow at the surface of the wick structure, and the vapor flow in CFD, that's a bit more challenging.
Okay. Let's keep going. Next one comes from Mark at CI. Why would I use one piece versus two piece?
Cost. It's cheaper. Yeah, that's the short answer.
Generally as well as the long one.
Yeah. Okay.
Here's another question on cost. Comes from Ranjith. Ranjith asks, on the cost reduction point of view, what are the parameters I need to consider to change from vapor chamber to heat pipe solution?
From a cost, so you have a vapor chamber. Yeah, so you have a vapor chamber solution, and you want to change that to a heat pipe solution.
Right.
The cost for the heat pipes themselves are generally lower in cost than for the vapor chamber. But you have to look at how many heat pipes you're going to need, and then what's the cost of installing those? Do I need to machine some fancy grooves into the base, or are they just straight grooves? Or in other words, how much is my machining cost going to be? And then you have to, press them in. You have to bend the heat pipes and press them in. So generally speaking, the heat pipe base heat sink is going to cost less than a vapor chamber, but not always. So you have to look at the cost of integrating the heat pipes into the base, whereas the vapor chamber is just one piece that's put on as the base.
Got it. Okay. And question from our friends over at Intel. Do vapor chambers allow bends in the XY plane?
Well, you can see from the pictures that we can bend them in the one plane. It gets much more challenging to bend them in the other plane. If I have a relatively long vapor chamber, I can do some bending before I flatten it. So it is possible. It's just not very common to bend the vapor chamber, in the long beam direction. So you can bend them in the thin direction, but not in the width direction.
Okay. Next up, question from Jack at Elbit. George, what's the best solder material and process to attach the HP or VC to an aluminum metal sheet?
Okay, the first thing you want to do is nickel plate the aluminum sheet, just because it makes the soldering a whole lot easier. The next thing you have to be careful of when choosing a solder, most of the solders are above the boiling point of the working fluid. For example, let's just use water, for example. When I'm going to solder above 100 degrees C, I start to have a positive internal pressure in the heat pipe or vapor chamber. Now, because the heat pipe's round, it can withstand a positive internal pressure without much distortion. Whereas my vapor chamber is a flat device. Flat vessels are terrible pressure vessels. So as I get to, say, 105, 110, or 120 degrees C, that internal vapor pressure is going to want to make that nice flat vapor chamber turn back to round. What we do is we design a fixture that holds that pressure, holds the vapor chamber flat during the soldering process. And we have a little technical paper on how to do that. So we can also offer that to anybody who wants it.
All right. I'm not sure we're going to get through all the questions that are coming in thick and fast. We are up to 33 questions in this presentation.
Whoa.
George, you obviously hit a a good note with everybody today. So they got lots of interesting questions. If your question doesn't get answered today, folks, don't worry. We will get back to you either through the system or through email. We'll connect you with George. We'll make sure everybody gets an answer one way or another. But let's for the benefit of the audience, let's hit on a couple of other interesting ones. This one comes from Tomas at Tomar Electronics. George, when you're talking about result accuracy, are you using the centigrade scale, Fahrenheit, K? What is it?
I think most of us use degree C. At least in the thermal business, degree C is the most common. I always use degree C.
Okay. Tyler asks, what encapsulated gases are used in most heat pipes?
Encapsulated gases. Well, hopefully none. All you want in there is the working fluid and the working fluid in its vapor phase. For example, water. What we normally do is we will put. There's a couple ways to process these things. I'll just walk you through one. You put the liquid, and it's just like a refrigeration system. You put the liquid into the device, and you draw a vacuum on it. What that vacuum does is it draws the air out. It also then draws out a little bit of the water vapor, and then you seal it off. So what you have is only the working fluid in there under a vacuum.
Okay. Question comes from Stephen at Rocor. How much of a role do you think CFD will play in advancing the design of the internal structure of vapor chambers?
That's a really good question. I think as you start to tweak these things to get out the last bit of performance, and as you start to look at different types of, say, nanostructured wick structures and things like that, I think CFD is going to be key in early on in the development of unique wick structures. But as far as using these things just to model the heat sink, that's done every day. But it's very uncommon to use CFD to model the internals of a heat pipe. So I'm not quite sure if that answers the question. But I do believe as you develop new unique wick structures, CFD will come into play for that.
Okay. Question from Raytheon. Thank you, George, for the presentation. You mentioned large diameters are possible for heat pipes, on the order of meters, I believe you said. How large have vapor chambers been made? How big can they be?
I'll just walk you through a couple examples. Vapor chambers, I think the biggest one I've seen is probably like the size of today's TVs, in the neighborhood of a sort of 47-inch diagonal or a couple feet by a couple feet. That's not a limit by any means. Heat pipes I've seen, the longest heat pipes I've seen are probably on the order of 10 to 20 meters, and probably the longest ones that are being used now are the ones for the transatlantic pipeline where they're keeping the ice frozen. So as far as vapor chambers, how big can they be? I don't think there's a real limit. The largest ones I've seen have been, between 5 and 10, say, square feet.
Pretty good size.
Yeah.
All right, we're getting down to... I think we can handle two more questions because we're almost up to 40 questions. I don't think I've ever hosted a webinar that had 40 questions, so that's pretty impressive. So let's try the last couple of questions here, George. How do you decide the area and length of the evaporator and condenser sections?
Well, the area and length of the evaporator is generally fixed by what you use, what you're trying to cool. If I have a 1-inch, 1 by 1 inch heat source, well then my evaporator is 1 inch. The condenser size is generally determined by how much heat sink I need. If I need 6 inches of a heat sink, well, then that's what you have for a condenser area. So the application generally dictates what those are.
Okay. And our final question for today, because we're a little bit over time. This is quite an interesting one. Comes from Tommy. Question in the application in data centers. Tommy says, this is for a data center application. If I have multiple heat sources on the server, can we route heat pipes from various heat sources to a central condenser?
Yes. That's quite common to do. You just have to make sure that you have enough capillary action to move the liquid past that first or second heat source to the third heat source. So it's very common.
All right. I'm sorry we couldn't answer all the questions, but if you ask a question, you will get an answer, either directly from George or through us in the next day or two. I just want to remind the attendees that the video recording of George's presentation will be available in the next hour or two very shortly. You'll be able to log in through the same link that you watched the live version. And a copy of the slides will be available automatically in 24 to 48 hours from now. Again, you'll receive an email from us to notify you when those are available. Thanks, everybody, from all around the world attending today. We had a quick look at who was here today: Toshiba, Honeywell, Microsoft, Facebook, Qualcomm, and GE, to name just a few. It was a really great presentation, George. Thanks to everybody who attended. George, thanks to you. Great to host you again, and we look forward to seeing Celsius at Thermal Live another time. We'll have another presentation on Thermal Live in the next hour. Thanks, everybody.
Bye-bye.